3.2 The Earthquake Processes. Though the Earth crust moves slowly on our timescale, it's pretty fast, geologically speaking. An active fault has moved during the past 10,000 years. Potentially active faults have moved between 10,000 years and 2 million years ago, but not in the last 10,000 years. And an inactive fault has not moved during the past 2 million years. Since we don't have historical records going back even 10,000 years, often the paleoseismicity of the fault must be determined, which means geologists look for clues on the fault or in the sediments disrupted by the fault to determine the last time there was movement along the fault. The earthquake cycle consists of several stages. These stages are based on observation and on the theory that there is a drop in elastic strain after an earthquake and a reaccumulation of strain before the next event. Strain is deformation from stress. An elastic strain is deformation that is not permanent. I am sure you are all familiar with stress and strain. Hopefully it has all been elastic strain and you have not cracked. The earthquake cycle is depicted in this series of images. No strain and no displacement. Elastic strain accumulates and deformation occurs. Rupture, earthquake occurs, and elastic strain is released. Elastic strain, bending, has been replaced by horizontal displacement, fault slip. What type of fault is this? Strike slip. So the earthquake cycle has 4 main stages. Stage 1 is a period of inactivity along a segment of fault. Stage 2 is a period of small earthquakes where accumulated elastic strain produces small quakes. Stage 3 contains foreshocks that occur prior to a major release of stress. However, foreshocks don't always occur. Stage 4 is the main shock and aftershocks, where the fault releases all pent-up stress. This is the major quake. The cycle is hypothetical and periods are variable, but stages have been identified for many large earthquakes. When earthquake occurs, seismic waves are generated. This is due to a release of energy from rupture of a fault. We've already talked quite a bit about them when discussing the internal structure of the Earth. 2 wave types travel through the body of the Earth. Body waves. They are P waves, primary or compressional waves, and S waves, secondary or shear waves. P waves move fast with a push-pull motion, as seen in this slinky image. Can move through solid, liquid, and gas, and it is possible to hear them. S waves move slower with an up and down motion, as seen in this wave image, and can travel only through solids. In contrast to body waves, surface waves move along Earth's surface. They travel more slowly than body waves, move both vertically and horizontally with a rolling motion, and are responsible for most of the damage near epicenter. Love waves, one type of surface wave, is a horizontal ground shaking which causes a lot of damage to foundations. No love from me. Not all earthquakes happen all at once. There are slow earthquakes where the strain never seems to build up big enough for a large all-at-once type earthquake. This is also known as tectonic creep. Tectonic creep, or fault creep, occurs when movement is gradual, such that earthquakes are not felt. It can produce slow earthquakes on the order of hours and months, as compared to seconds and minutes for fast, normal earthquakes. It can slowly damage roads, sidewalks, and building foundations. The magnitude can be between magnitude 6 and magnitude 7, which is quite large, but not even felt because it is so slow. 3.3 Earthquake shaking. There are many earthquakes in any given day. They are compared based on magnitude, the amount of energy released, and intensity, the effects on people and structures. Magnitude used to be measured and compared based on the Richter scale, but now moment magnitude is used. Moment magnitude and Richter scale are approximately equal. Both scales are logarithmic, which means based on powers of 10. For example, ground displacement for a magnitude 3 earthquake is 10 times that of a magnitude 2. Ground motion is measured by seismograph, and the motion is related to magnitude, depth, and geologic setting. This table shows that larger earthquakes are less frequent than smaller earthquakes. Remember, magnitude is inversely related to the frequency from Chapter 1. Approximately 150 very minor earthquakes, moment magnitude less than 3, occur every hour. Compare that with great earthquakes, moment magnitude greater than 8, occur only about once per year. Here are some examples of seismographs, which detect and record seismic waves. It's basically an arm or a spring that amplifies vibrations. Earthquakes are mapped according to epicenter, which is directly above the focus where the earthquake actually occurred in the earth, i.e. the focus is directly below the epicenter. The moment magnitude is determined from the area of rupture along fault, the amount of slippage, and the rigidity of the rocks. Here are some motions to remember the 3 parts to determining moment magnitude. Rigidity, or strength of the rocks. Ooh, I'm strong. Area of rupture. Draw the area of a shape. Amount of slippage. Hands slipping by. Again. Rigidity or strength, the rocks. Area, ruptured. Amount of slippage. Though the scale is logarithmic, the rate of change in ground motion is different than the rate and change in the amount of energy released, as indicated in this table. With a change in 1 unit in moment magnitude, the ground motion change is 10 times. But the energy change is 32 times. Earthquake intensity is measured on the modified Mercalli scale. It is a qualitative scale, 1 through 12, based on damage to structures and people's perceptions. Modified Mercalli intensity maps show where the damage is most severe. This table describes the effects of the earthquake for the different intensity ratings. It goes from not being felt by many at level 1 to felt by all at level 6, to total damage at level 12. Shake maps use seismograph data to show areas of intense shaking. These shake maps are for the 1994 Northridge, California moment magnitude 6.7 earthquake and the 2001 Nisqually, Washington moment magnitude 6.8 earthquake. These earthquakes have similar magnitudes, but the shake maps show much more intense shaking in the Northridge earthquake as compared to the Nisqually earthquake. Why might this be? Take a moment of pause to jot down some of your ideas. There are several possible answers. Some good ideas would be that the sediments and rocks are different, such that they may transmit the seismic waves differently, or the map scale only looks like there was more shaking in California. But the main reason is probably that the earthquake focus was deeper under Nisqually epicenter than the Northridge epicenter, and so the seismic waves were more attenuated in Washington. Here are some scenario shake maps for the Boise, Idaho area. If the Squaw Creek Fault were to rupture with a moment magnitude of 6 and 7. As you look at these maps, do you think you would be okay in these scenarios? How about our communities? Do we need to employ more earthquake mitigation strategies in the Boise area? During an earthquake, shaking experience depends on earthquake magnitude, obviously, but also location in relation to the epicenter, direction of rupture, and local soil and rock conditions. The farther a location is from the epicenter, the less shaking occurs. Both types of body waves are emitted from epicenter of quake. Seismographs record arrivals of waves to station site, and a seismogram shows the record of the waves. P and S waves travel at different rates and arrive at station at different times. That difference in arrival time is used to calculate a distance to epicenter. These two images show seismograms with the arrival of first P waves, then S waves, and then L or surface waves. The blue image shows seismographs at increasing distances from the epicenter. As the distance increases, the difference in the time of arrival for the waves also increase. Note that the wave amplitudes are not to scale, i.e. the surface waves were not significant in Colorado or Columbia. To find the epicenter, at least 3 stations are needed. Distances from epicenter to each station are used to draw circles representing possible locations. The place where all 3 circles intersect is the epicenter. The process is called triangulation and is depicted in this image. The depth of the focus of the earthquake also influences the amount of shaking. Remember that the focus is the place within the earth where the earthquake starts. The deeper the earthquake, the less shaking at the surface due to a loss of energy, which is called attenuation.